In this video, we're going to consider uncertainty as a shape, a picture of what you believe to be true. Imagine you're sitting in your office and your supervisor drops by and says, "How long would it take you to update the district's emergency management plan?" And your response is, "I don't know anything about the emergency management plan. I have no experience with it. I didn't even know it exists. I have no data. I have no idea how long it would take." So perplexed, you go to seek help from an experienced coworker. And it turns out that this coworker begins by asking you a couple of questions. And the first one is it going to take between minus infinity and plus infinity? And you smile and say, "Of course not. It's certainly not going to take me minus infinity. Is it going to take you plus infinity? Can we do better than that?" And you say, "Yeah, I think we can." So your coworker says, "Can you get it done this year?" And you say, "Yes." So the coworker then says, "Okay, so then we have a maximum of 365 days. You can do it in a year. Can you get it done right now?" And you say, "No." Then the question might be, well, if you had nothing else to do, if you had absolutely nothing else to do, how quickly do you think you could get it done? Something that you know nothing about. Well, I'd have to learn about it. I have to see a model. I have to figure it's going to take me at least 45 days. So we have a minimum now. And we have a basic idea that it's going to take between 45 and 365 days. So we've already narrowed it down from minus infinity to plus infinity to between 45 and 365 days. Do you know anything else? Is any other time frame in there more likely than any other? And you say no. So we're going to draw a picture of your uncertainty. And I'm not going to be teaching the use of at-risk. That comes in other videos. I'm going to be using it here. So I'm going to go up here to distribution because I know what I want to do. I want a uniform distribution, and I'm going to get that from the continuous palette here. So I'm going to scroll on down till I find uniform, and there it is. I click on it, and it comes up as this shape here. You see it's a flat shape. It's just a rectangle. The default values are minus 10 and 10, and I want to substitute my minimum. So I'm going to put 45 in here, and I'm going to put 365 in here. And now we have a picture of your uncertainty. This is what you believe to be true. This is a picture of how long it will take you to complete an emergency management plan. And you're looking at this and you're thinking, my boss isn't going to be happy with this if I tell her 45 to 365 days. I think she would like to have it done within 100 days. Well, then we have the opportunity to find out how likely that is given your uncertainty. So I'm going to go up here and I'm going to type in 100 days. And I see this is 17.2%. Let me get this scrolled over here. There's an 82.8% chance that it's going to take more than 100 days. So I want you to pause a second and think of what we've just done. You were asked about a task that you had no information about, and you quickly were able to bound it between 45 and 365 days. Now, with a bound, you know that's not going to satisfy your boss because your boss wants a number. You don't have a number. You're saying everything in here is as likely as anything else. That's what makes this a flat top distribution. So what you can do, though, is you can ask your boss, "What's your number?" The boss says it's 100 days. You can plug this in here and you can say, "Well, I think there's about an 83% chance it's going to take more than that, but I'll give it my best shot." Now, is this junk? Is this useful? Consider it compared to the alternative where the boss says, "How long is it going to take you?" And you say, "I don't know." And they say, well, how quickly could you have it done? "I don't know." "How long?" And your answer is, "I don't know, I don't know, I don't know." And here we have begun to deal with the uncertainty and to try to quantify it a little bit. But what we're doing is we're giving it a shape. We're saying this is a picture of what I believe to be true. So let's close this picture and let's come on down here and let's play the same game again. A minimum of 45 and a maximum of 365 days. Do you know anything else? Well, I know the boss would like to have it done in 100 days. And as I've thought about it, I thought, if I can get an example, yeah, I can have it done in 100 days. So here are our parameters. Let's go back up here and I'm going to delete this and I'm going to say equal sign, risk triangle, left parenthesis, and I'm going to say take this number, comma, this number, comma, and this number, right parenthesis, and here is a picture of my uncertainty. Now we have something a little bit different. Well, quite a lot different, actually. Before we had a rectangle, and now we're saying, well, it's between 45 and 365. So we have chosen a portion of the number line. We have bounded it and said it's somewhere in there. And then imagine the computer is saying, do you know anything else? And I say, yeah, I know that 100 is the most likely. So I grab 100 and lift it up. I get my ruler, connect the dots, and this is a picture of my uncertainty now. What this is doing that we didn't have before, remember that, imagine that uniform distribution here where a straight line going up to here and all the way over to here and a straight line down. These areas in here, this likelihood, we're saying, no, it's not so likely, actually. I don't think, it could take as much as 365 days, but it's not so likely anymore. The shape is telling you, the height of the bar is telling you how likely these different numbers are. So this is a shape of our uncertainty. It's quite a bit different from what we had before. Okay? So let's copy these. Down to here, and we're going to take a look at a PERT distribution now. So I'm going to go up here, delete this. I'm going to go back to the distribution icon. I'm looking for a PERT. And I click on this. And the PERT has 3 parameters, a minimum, which is 45, a most likely, which is 100, and a maximum, which is 365. And so here we have essentially the same segment of the number line from 45 to 365. And if I want to show that, I'm going to hit a right mouse click, graph options. I'm going to go up here to the x-axis and I'm going to say, give me the right to change this, and let's make it 400 so we can see the end of our distribution. So now we can see that it ends at 365. Do you know anything else? Yeah, I know 100 is the most likely, so I raise that up. But instead of a ruler, I get out an old French curve, a bendable curve, and I connect these dots. Now, that's not literally what happens. The software is drawing this for you using some mathematics that's built into the software. But this is a little bit different picture of what we had with the triangle. So let me show you. I'm going to overlay a triangle here. I'm going to scroll on down, pick the triangle. And here is the graph that we had a minute ago, and here is the new graph. So the blue is the PERT distribution. They have the same parameters, the same minimum, most likely, and maximum value. But you can see how they have different shapes, and these different shapes are reflecting our belief about what's true. So if I think it's more likely going to be close to the lower end of the scale, to the 45 days, the 100 days, 150 days, and less likely to be a long time, close to a year, then this blue shape better represents my belief than the red shape does. You can notice that the red shape gives a lot more likelihood, area under the curve, to the long-term period of time that it would take. So we're working without data here. This is you expressing your beliefs. You are trying to characterize your uncertainty. And so one way that we do that is with shapes. We've looked at a uniform distribution, which is a rectangle. We've looked at a triangle, and we've looked at sort of a curved off triangle. Okay? These are different ways that you have to express to other people what your uncertainty is. Or a group of people could arrive at a shape and say, this is what we believe our uncertainty is. So let's copy these parameters down again, and I'm going to copy them in here. And we have something called a trigen. So I'm going to scoot this up for us a little bit. And here, instead of a minimum and a maximum, we have a bottom and a top. So let's go back up to our distribution here, a picture of our uncertainty, and let's click on the distribution. And I'm going to clear the overlays, and I'm going to matter of fact, let me just delete this. I think that might make it easier for you to follow. So let's go back up to the distribution here. And this time I'm looking for something called a trigen. And a trigen has a bottom. And I'll explain this in a second. And we're going to put in our 45 days in the bottom. Our most likely is going to be the 100 days. And the top is going to be 365 days. So you would use a trigen distribution when you really don't know what the absolute minimum is or the absolute maximum. It might be more or it might be less than you have. So you're saying my bottom estimate is 45. I don't know if it's a minimum, but it's going to be my lowest number, the lowest number I feel comfortable with. And my top is 365. Now, what you can do here, and this is a bit advanced, but no worries if you don't follow it right away, is you're saying, okay, so what's the percentile value that you gave? Your bottom, what do you think it is? It's not an absolute minimum. If you think it's about a 10% percentile, we'll leave that right where it is. The top, I think, I don't think it's going to be more than a year. I'm going to make that the 99th percentile. And so I'm going to click on this. And here's what I would like you to see. The computer goes ahead and it calculates a minimum for you. So look up here. It says, all right, so the absolute minimum is minus 29.77. And the absolute maximum is 401. Well, minus 29.77, that makes no sense at all. So I'm not very happy with that. So what I'm going to do is I'm going to say, all right, let's make it a 2% chance that it's less. And so at 2%, now I've got something that at least makes sense. It's between 20 days and 398 days. So what this trigen does is it adds tails on to what you have. That's not something that you're going to use right away, but it's something to keep in the back of your mind. There's one more distribution, one more shape that we're going to talk about, and that's the beta general. And we're going to go back to 45 and 365. So we're going to come up here. I'm going to delete this. We'll go to our distribution, define distributions, and I want a beta general, so I'm going back up to the B's. I click on the beta general, And the beta general says, give me a minimum, that's going to be 45. Give me a maximum, that's going to be 365. And I click on this, and it returns this shape automatically. Now, it does that because it has default values in here for this thing that's called alpha 1 and this thing that's called alpha 2. But if I change these, I can shift the shape. So let's make that a 10. And you see this shifted all the way over here to 365. So if I use the parameters of 2 and 10, that would reflect my judgment that it's going to be a whole lot closer to 365 days. By the way, let's see if we can extend that number line a little bit. So we go to the x-axis again. I want to say, let's start at 0. Let's go up to 380. Yeah, that's okay because that's more than 365. So there's our entire number line now. Now I'm thinking, now that's not exactly what I think. I think, let's see. How about if we make that a 5? And you can just play with this and see what happens. So if I go to, let's make this a 2. And let's make this, I don't think it's going to take too much time over there. Let's make this about a 8. And I'm just picking numbers. And I look at this and say, yeah, I feel pretty comfortable with that. This is a picture of my uncertainty. Yeah, it could be something that takes, more than 285 days, closer to a year, but that's very unlikely. This is a picture of what I believe to be true. Okay, so there are distributions here that you use when you don't have data. What you have is some judgment, some experience, some gut feeling. But what you're doing is you are describing to people in a numerical way what you believe an uncertain value is. This can be used for knowledge uncertainty, natural variability. Just think of it as characterizing your uncertainty with a shape. So I'm going to give you one more thing to do. I'm going to attach this file that you can play with if you like. And I'm clicking on the Flat Distributions tab now. And up here in cell B5, if we take a look at this, I have a flat distribution. This one has a minimum of 0 and a maximum of 1. Okay, and this flat top is saying any number between 0 and 1 is as likely as any other. So the uniform distribution is something that's used when you have maximum uncertainty. This is characterizing your uncertainty. In this particular exercise, we have a uniform distribution here plus a uniform distribution here. And here we sum these two numbers. So here's what I would like you to see. I'm going to do a simulation here. I'm going to calculate this 10,000 times so we don't have to spend too much time watching. If you have two flat numbers and you add them together, what do you get? Well, it looks like we're not going to get a flat number in return. If you're adding them together, you're going to get a triangular number. And if we did lots and lots of iterations, recalculations of the model, this would be perfectly triangular. It would work out all these little chance events that occurred because of the size of our sample. Let's take a look at what happens when you multiply two flat distributions together. It looks like we're getting half of a triangle. Okay, so when you have uncertainty, the unit value of a uniform distribution between 0 and 1 is a shape that can be used to create all other distributions. So let's scroll on down to here. Here I have 5 uniform distributions. Take a look up here in the formula line. You can see The formula is the same for each one. And in each cell, you are getting a random number pulled from that distribution. They are not related to one another. And then we're going to add them all up. So here I have 5 uniform distributions, 5 squares. I'm going to run a simulation of 10,000 iterations. And I see the triangle is kind of rounded off here. And really what's happening, if I did this 100,000 times, this would be a normal distribution. You would be looking at a normal distribution right now. Let's take a look at the multiplying 5 square numbers together. This distribution you might not recognize, but it's a log normal distribution. And here's the punchline for this. All the distributions that you're going to be seeing in this course are basically made up of different mathematical combinations of that flat number, that rectangle that we started with. As it turns out, there are variables that do seem to be the result of adding a lot of random values. So if we're talking about, let's see, anything biological, there's the effect of genetics and diet and environment and all those kinds of things. And so things that are any kind of variable that is biological tends to be, let me see if I can pull up those results again, tends to be normally shaped. In nature, we have things, physical things, that affect one another. The wind blows against the rocks, the water blows against the rocks, and there are all kinds of factors acting on the rocks to weather them. And it turns out that as a result, a lot of physical things, a lot of physical phenomena in nature have a log normal distribution. That means there's a lot of little tiny rocks and relatively few gigantic Rock of Gibraltar rocks. This log normal distribution describes a lot of physical things. There are a lot of soft winds and very few very, very strong winds. So you're going to find out as you go through this class and as you go through your own discipline that there are variables that tend to have different kinds of distributions. And that's because they all start with this flat number here. They have many different flat numbers that might go into a determination, like the price of a house. This is what it costs. Imagine that this is what it costs to dig the foundation, and imagine that this is a number, for the concrete pouring, and that this is a number for the wood frame, and this is a number for the roof, and this is a number for the, this and that. And so a cost that is the sum of many different things tends to have a normal distribution. And so we're going to, hopefully you're going to learn a bit about that sort of thing as we go through here. But I want you to understand that these are shapes that are defining the uncertainty for us. We started off with an example where there was no data. Here we're using data and saying the data tend to drift toward certain shapes at times. And this has been an example of that. Let me close here so I don't run on. And if you've got questions, feel free to ask in class.